Hello everyone, this is Professor Roman. Welcome to the 43rd video in my video lecture series, An Introduction to Discrete Mathematics. In this video, we'll continue our discussion of graph theory with Eulerian and Hamiltonian graphs. One of the most common problems in graph theory is that of finding a specific trail or path in a given graph. So, for example, in the communications graph that we saw way back in example 407, and let me temporarily paste that graph in here, a path from one vertex to another represents a way to send a message from one government to another, possibly through intermediate governments, friendlier governments. So, for instance, the government of Mongolia can send a message to the government of Russia, but it will have to go through China and the United States before it reaches Russia. As another example, a trail in a transportation graph represents a route from one city to another that does not use any highway more than once. That is clearly an important problem. You don't want, if you're running a trucking company, you don't want your trucks to cover the same road more than once just to get from one place to another. These sorts of questions have immense implications to urban planning and economic considerations for companies. Their importance really can't be understated. Companies like UPS and FedEx and the post office all have an abiding concern in dealing with questions like this. Even the Königsberg Bridge problem that we stated earlier can be stated in terms of trails. The problem amounts to whether or not there's a closed trail, also called a circuit, in this graph that covers every edge of the graph. So it will therefore cover every edge exactly once. And as we saw, there is no such circuit. Now, it's easy to see how we can use the concept of a circuit to generalize the Königsberg Bridge problem. And in honor of Leonhard Euler, who is considered one of the founders, if not the founder, of graph theory, an Eulerian circuit in a connected graph G is a circuit that uses every edge of G, and therefore uses every edge exactly once. If a graph G has an Eulerian circuit, it's called an Eulerian graph. Now we can generalize the Königsberg Bridge problem by asking the following questions. Is there a simple way to tell whether or not a connected graph is Eulerian? And second, if we know that the graph is Eulerian, is there a simple way to actually find an Eulerian circuit in the graph? Well, fortunately, this is an easy problem. We're kind of lucky in that respect. Earlier in this course, I showed that no Eulerian circuit in the Königsberg graph could exist by reasoning that if there was such a circuit, then all of the vertices would have to have even degree. You have to enter and leave every vertex. So the degree accumulates in pairs, in multiples of 2. And that happens to be the case for any connected graph, as we're going to see in a minute. Also, the converse of this statement is true. Every connected graph, all of whose vertices have even degree, has an Eulerian circuit. Incidentally, as to the pronunciation of this word, in German, EU is pronounced oi, so it would be Eulerian, Eulerian, which is the way I've been pronouncing it. In English, there's a temptation to pronounce this Eulerian, and the E would be silent, Eulerian. And both seem to be in somewhat common usage, so you can decide how you want to pronounce the word. So let's examine this theorem. A connected graph is Eulerian if and only if all of its vertices have even degree. So as to proof, let's first suppose that a connected graph G is Eulerian and show that all of its vertices must have even degree. This is the easier half of the proof. Well, just imagine traveling along an Eulerian circuit in G, and let's start at the middle of one of the edges, not at a vertex. It might be a little simpler to see what's going on. And then we're going to return to that same point. Each time we pass through a vertex, we contribute 2 to the degree of that vertex. We come into the vertex on one edge, we leave the vertex on a different edge, so we contribute 2 to that degree. So since every edge appears exactly once in the circuit, every edge is going to contribute to our count as we travel through the graph. So the degree of every vertex is the sum of a certain number of 2's. And so it's even. The converse is a bit more work. We want to show that if a connected graph has vertices of even degree, all their vertices have even degree, then the graph has an Eulerian circuit. Well, we can describe an algorithm for constructing an Eulerian circuit in G in the following way. And the details are a little bit involved, but it's a simple idea. It's just sometimes simple ideas are hard to put in words. We begin by finding a circuit in G. So every edge is used exactly once, but it doesn't necessarily include all edges. And so that's not a very difficult task, and I'll talk about that in a minute. And then we increase the size of that circuit if it doesn't cover all the edges, and combine circuits until we get an Eulerian circuit. So here's how that goes. To find the first circuit in G, we can simply start at any vertex V and travel along different edges, never using the same edge twice, until we return to V. And we know that this is possible precisely because every vertex has even degree. So we can't get stuck anywhere. To get stuck at another vertex would mean we may have gone through that vertex several times already, but we get to the vertex and we can't get out. Well, we came in along an edge. That would add 1 to our count of degree for that vertex and would make it now an odd degree. So we know there has to be one more edge we haven't used yet because we know the degree of the vertex is even. So we can never get stuck in a vertex. So we start at V, we travel along however we want, as long as we don't duplicate an edge, we will eventually get back to V. And so we will have a circuit, and I've drawn it here, called C, and it may or may not include all the edges of the graph. Okay. if C happens to contain all the edges of G, we're done. We've got an Eulerian circuit. But if not, then we have to take a look at the subgraph, which I called H of G, obtained from G by deleting the edges of the circuit we just found. So we'll yank out these edges here. We'll yank out C from the graph and call the remaining graph H. Now H may not be connected. We may have pulled the whole thing apart, but it still has the property that all of its vertices have even degree, because by removing C, we have removed two edges from each of the vertices in C. And so we've dropped the degrees by 2, and so we still have even degree for every vertex. I should have made it a little bit clearer. We're removing the edges of C. I said that in writing, but I didn't say that in words. So we're not taking out the vertices, just the edges. Okay. So that's gonna drop the degrees, but by 2 for each vertex, so there's still even degrees. Now, since G is a connected graph, and we're assuming that, some of the edges of H, the remaining edges, after we pulled out the edges of C, some of those edges must meet the circuit C somewhere. Otherwise, C would have been in its own connected component, and there would have been other connected components. So you can see from the figure here, some edges in H must have met a vertex that was on C. Well, now we can repeat what we just did starting at U here. We don't have these edges anymore, and we set out to find another circuit. Same principle applies. We have a graph, not necessarily connected anymore, but that doesn't matter. We have a graph in which every vertex has even degree. So if we start out from U, eventually we will have to come back to U. Well, now we can piece these two. Here's a better picture of that, that new circuit in H. But now we can piece these two circuits together. We can start at V, we can move along here, and as soon as we hit U, we can switch over to the other circuit, follow it along, come back to U, and then finish the first circuit. So we've simply increased the size of the circuit, or the length of the circuit, and we've added more edges to it. So this can continue. Now we have a bigger circuit. We can yank these edges out and look at what's left, and they will have to, if there is anything left, we can repeat the argument and enlarge the circuit even more. Eventually, since this graph is finite, we will have an Eulerian circuit. If that argument was a little vague, you're not quite following, not to worry, it's not surprising. It's a little bit of a delicate argument. It takes a little bit of imagination. One of the important things in trying to learn graph theory is to use your imagination as much as you can to try to picture these things in your head as well as on paper. It's big. It really will help if you can do that. So if this argument seemed a little vague, draw some pictures. Go over the argument a couple of times. With respect, this is not a difficult argument. The problem is just getting the idea in your head. Okay, so let's look at a couple of examples. Consider this map here. So we've got a river with 3 islands and a bunch of bridges, and we have the 2 shores, A and E. Similar to the Königsberg problem, but a little more complicated. Is there a way to make a round trip through the islands in this map, crossing each bridge exactly once? You know, this is in some sense a frivolous question. You know, it's not that important, but one thing you should keep in mind is that this is just a simple example of a very important concept when it is applied to transportation networks and the like. It becomes an extremely important problem in real life, practical problem. So this is kind of just a fun way to express the problem. Well, in order to deal with this question, we represent the topography here with a graph, and each vertex represents a body of land, either an island or a shore, and the edges represent bridges. Now, the degree of each of the vertices in this graph is even, unlike the Königsberg problem. And so we know that there is the graph is Eulerian, there is an Eulerian circuit. To find such an Eulerian circuit, we can follow the steps in the proof of the previous theorem. So we'll pick any vertex, may as well be A, and we will trace edges until we return to A. So we could go from A to B, and then B to C, and C to A. You know, in this simple graph, it's probably possible just to trace the entire Eulerian circuit, but remember that the graphs will be a whole lot more complicated in practical applications. So we just take it one step at a time. E1, E3, E2. So that's here. That's the black subgraph. Now, since this is not all of the graph, we can expand this circuit. We come from A to B, and at B here we can take another path. So don't use the black edges now. In the proof we would have actually removed them, and we would have found this circuit here. So E1, E4, E5, E3, E2. That attaches the red circuit to the black circuit. Okay. E1, E4, E5, E3, E2. So we now have the black and red together, and that is a circuit. It's not a cycle because vertex B is used more than once. Okay. But it is a circuit, and we're headed towards an Eulerian circuit. Okay. So we still haven't got the entire graph, we haven't got the blue edges, but if we erase everything else, there's an obvious circuit in the blue edges, and that would be E8, E7, E6. So we could attach that to the red-black circuit at vertex D, for example. And we would have E1, E4, E8, E7, E6, E5, E3, E2. That is an Eulerian circuit. Another example, in this graph, the vertices represent cities and the edges represent highways. So it's a transportation graph. Is there any way to start at any city and make a round trip that traverses each highway exactly once? Well, The answer to that question is yes, because all the vertices have even degree, so the graph is Eulerian. We're lucky there's such a simple test for Eulerianness. It's going to get a lot worse before it gets better. And to find such a round trip, we need to find an Eulerian circuit. So to do so, we can pick any vertex, say V1, and find a circuit. So we can go along E1, E3, and E2, and that is a blue circuit. And then we observe that the black edges do meet the blue edges at, for example, V2. So we can find a circuit of black edges, E5, E8, E7, E6, E4, and we can attach that at V2. So we would go from, let's see, I've written this a little differently. It doesn't matter what order you write the edges, it's still an Eulerian circuit. E3, E2, E1, E5, E8, E7, E6, E4. And that starts and ends at V2. Okay. Now, while this procedure, this algorithm for finding an Eulerian circuit when the graph is Eulerian, is pretty straightforward, it does become a bit tedious when the graphs get large. There are other approaches to finding Eulerian circuits. The most famous one is known as Fleury's algorithm. And in some cases, this is easier to apply than the method I've just used in the last two examples. So here is the algorithm. It's pretty straightforward. Let G be an Eulerian graph. Then an Eulerian circuit can be obtained for G using the following instructions. 1. Start at any vertex and traverse the edges of G, erasing edges as they are traversed. Or you can just ignore them, but you can't use them again. Okay. Also erase any isolated vertices as they are created by removing edges. Never choose an edge that is a bridge unless there's no other choice. And remember, a bridge is an edge whose removal increases the number of connected components. In other words, it breaks the graph down even more than it was before. Okay. If it was connected, you now have 2 connected components. If there were 10 connected components, you pull out the bridge, you now have 11 connected components. So you can wander willy-nilly through the graph, never using an edge twice, and never choosing a bridge unless there's no other choice. The trick, of course, is knowing which edges are bridges. So this doesn't remove all of the complications that exist in the previous procedure. Okay. So let's give it a try. On the graph in figure 146. So that was this guy. And just what I'm going to do here is copy this just temporarily and say I'll stick it right here so you can see it at the same time. Okay, so we'll begin at vertex V. It should be V1, I presume. And remove edge E1. And what I've done is I've just made it a very faint line. I hope you can see it. rather than erase it completely so you can see where it used to be. And I would only do this once, just for the first time you've seen this. Okay. So we remove edge E1, and then we remove edge E3, and that leaves us here at vertex V3. So this is what the graph now looks like, and I can get rid of this. Now we've got several choices for the next edge. We're sitting here at V3. We could remove E2, E7, or E6. But E2 is a bridge. If we remove E2, we will isolate vertex V1, thereby increasing the number of connected components from 1 to 2. In other words, the graph is connected now, but if I pull out E2, it's no longer connected. So according to the algorithm, I cannot choose E2. So I'll choose E6. So that pulls this edge out, still connected. Now we are sitting at V4. I could pull out E4, and that is going to disconnect. It's the only choice I have. It's the only edge left connected to V4. It is a bridge. It will disconnect. It will isolate V4, but the algorithm says you can choose a bridge if you have no other choice. We have no other choice. We choose E4. We have no other choice, so we choose E5, and then E8, and then E7, and then E2. And that is an Eulerian circuit. Another example, here is the floor plan of a certain mostly unlivable house. Is there a way to start in any one of the rooms or outside the house and make a round trip through the house that goes through each doorway exactly once? Well, to answer this question, we need to represent the floor plan by a graph. And here it is. The vertices of the graph represent rooms, and vertex A represents the outside. Each edge represents a doorway. So a round trip through this house that goes through each doorway exactly once corresponds to an Eulerian circuit in this graph. Every vertex in the graph has even degree, so the graph is Eulerian, and we can use Fleury's algorithm, for example, and one circuit it will produce is this one. It's just one way to write the circuit. There's only one Eulerian circuit in the graph. It's just a question of how you describe the edges, in what order you write the edges. Okay. Now, as a slight variation on this question of the existence and construction of an Eulerian circuit, it often happens in applications that you have a graph and you have two distinct vertices, U and V, and you want to know whether or not there's an open trail in G from U to V that uses each edge in the graph exactly once. It's not quite an Eulerian circuit because it's missing one edge, the edge from U to V. This is called an Eulerian trail from U to V, or between U and V. And there is a corresponding theorem whose proof I leave for you. Let G be a connected graph, and let U and V be distinct vertices in G. Then there is an Eulerian trail in G from u to v if and only if the degrees of u and v are odd and the degrees of all other vertices in G are even. This is a very short couple of line proof. So here is a street map. Each edge represents a street. Each vertex represents an intersection. And suppose it is your job to deliver the mail to each house along these streets. You want to start at the post office, which I've labeled here as A for post office, and finish at your house, B. Naturally, you would want to find a route that covers each street exactly once. You have to cover each street to deliver the mail. You don't want to go down a street more than once. Well, since the degrees of A and B are odd, and the degrees of all the other vertices are even, there is a way to do that. There is an Eulerian trail between A and B. How to find such a trail? Well, all you have to do is add a temporary edge between A and B. Now all the vertices have even degree. Use either of the two procedures we've just been discussing, either piecing together circuits until you get an Eulerian circuit, or using Fleury's algorithm. And once you have the circuit, pull out that temporary edge, and you have your Eulerian trail. And I just gave away the proof of the previous theorem. Finally, for this section of the book and for this video, I want to take a look at a problem that's similar to that of determining whether a graph is Eulerian. And this is the problem of determining whether a connected graph has a cycle that uses each vertex exactly once. Such a cycle is called a Hamiltonian cycle after the Irish mathematician Sir William Rowan Hamilton. And any graph that has a Hamiltonian cycle is called a Hamiltonian graph. So this is in parallel with the Eulerian case. In 1851, Hamilton invented a game, which is called Hamilton's Puzzle. And it involves trying to find a Hamiltonian cycle in this graph. And that's why the term Hamiltonian cycle is named after Hamilton. The vertices of this graph represent cities, and the object of the game is to find a round trip that covers each city exactly once. Now, although determining the problem of whether or not a graph has a Hamiltonian cycle is similar to that of determining whether a graph has an Eulerian circuit, this problem is much harder. And I say that because no one has ever been able to find a reasonable criterion for determining whether or not a graph is Hamiltonian. It's still an open question and one of the major unsolved problems in graph theory. It would have significant applications if it could be solved. I mean, you can always go through the graph and consider all the possible closed walks and see which ones might be Hamiltonian cycles, but that's not a practical solution if the graph has any size at all. So, in any case, even though we can't solve this problem, considerable progress has been made over the years. And I'm going to walk you through one particular result. And we're going to try to reason this out together slowly because the argument's a little bit intricate. So it goes like this. It seems intuitively clear that the more edges a graph has, the more likely it is to be Hamiltonian. More edges mean more paths, after all. So let's fix an integer n greater than 3 and consider a non-Hamiltonian graph h with n vertices that has the most edges possible without being Hamiltonian. So we add one more edge, you now have a Hamiltonian cycle. Since there are only a finite number of graphs with n vertices, we can do this in theory. This is not a practical consideration, this is theoretical. Since the complete graph, k sub n, is Hamiltonian, and I will let you sort that detail out, we know that h is not the complete graph, so it's missing at least one edge. And as I just said, if we add any edge to h, the resulting graph will be Hamiltonian because of the way h was chosen to have the most number of edges without being Hamiltonian. So let us add an edge to h. We'll pick two non-adjacent vertices, which must exist because the graph is not the complete graph, and insert the edge. So u and v are the vertices. We'll insert the edge uv just temporarily. That will give us a new graph, h prime, and that graph is Hamiltonian. And so it has a Hamiltonian cycle. That Hamiltonian cycle, which I'm calling C, must include the edge uv, the new edge. Otherwise, there would have been a Hamiltonian cycle in the original graph H, but there's not. So C does include this new edge. What happens now if we take away that new edge? So we're back to the graph H. The Hamiltonian cycle now becomes an open Hamiltonian path. It still touches every vertex exactly once because we're just removing an edge, but it's no longer a cycle because now it's an open path. So I'll call that path P, and it goes from U to V in potentially several steps. Okay. So all this fuss of adding and removing an edge was simply to show that the graph H, which is rather unusual because it's non-Hamiltonian but has the most possible edges, has a very specific structure. It has an open Hamiltonian path between two vertices, U and V, so every vertex of H is on this path exactly once. There certainly can be other edges in the graph G, but I'm sorry, in the graph H, but we've got all the vertices. So it's this black center here, the vertices and the edges that form the path P. Okay, now there is no edge from U to V. There wasn't when we started. We put in an edge, but we took it out. However, there are still many possible, and I say possible, ways to try to construct a Hamiltonian cycle using this path P. They must all fail because H is not Hamiltonian. So, for example, if, and I say if, the graph H had an edge from U to, let's say, U sub I, another edge in H, all the edges go between two of these vertices because these are all the vertices. If there's an edge from U to U sub I, then I called it E here, there cannot be an edge f from V to u sub I minus 1, the one before u sub I. Why? Because if this edge, which I drew as a dashed curve, were to exist, we would have a Hamiltonian cycle. And I've drawn the instructions to follow the cycle in blue. Start with U, traverse these edges until you come to UI, then traverse these edges till you come to V, then follow this edge F, if it exists, to U sub I, then go back here to U, and you have a Hamiltonian cycle. Since that cannot exist, H is not Hamiltonian, this edge F cannot exist. So, in short, if E exists, F cannot exist. That applies also, of course, if E just stretches from U just to the first vertex U2, then F would be an edge from V all the way back to U, which we know doesn't exist on different counts anyway. Okay. So what does this tell us? Well, it tells us that H cannot have too many edges. There are restrictions on the number of edges, but we have to be more quantitative about that. There are degree of U edges emanating from U, and they all must go to one of these vertices, because that's a complete list of vertices. For each of those, there is a forbidden edge F. Therefore, since the maximum number of edges emanating from U is n minus 1, could be an edge to each of these other vertices, the number of edges, and these forbidden edges all come out of V. So the degree of V has to be, it could be at most n minus 1, but we have to take out the degree of U, because for each of those edges that count in the degree of U, there's an edge that cannot emanate from V. So we get this inequality. And we can rearrange things here, which says that the sum of these degrees is less than or equal to n minus 1. That's quite a reduction in degrees, because potentially each of those vertices could have degree n minus 1. But we are now saying that the sum is less than or equal to n minus 1. So put this argument in reverse. If a simple graph has the property that the sum of the degrees of every pair U and V of non-adjacent vertices is greater than or equal to n, then the graph has to be Hamiltonian, because it violates this restriction. That's an argument you may have to go over a few times. It's a bit subtle. So this is a famous result from 1960 from a graph theorist named Osteen-Ore. I'm not sure how you pronounce his last name, Ore or Ora. Anyway, I think it's Ore. If a simple graph G with n greater than 3 vertices has the property that the sum of the degrees of every pair of distinct vertices is greater than or equal to n, in other words, there's a fair number of edges then the graph must be Hamiltonian. Euler's theorem has a corollary. A simple graph G with n greater than 3 vertices is Hamiltonian if the degree of each vertex is greater than n over 2. And I'm going to leave it for you. This is a result of Dirac. Leave it to you to show that this follows from Euler's theorem. Now, both of these theorems give sufficient conditions for a graph to be Hamiltonian. If the conditions hold, the graph will be Hamiltonian. But they're not necessary conditions. So put another way, a graph may be Hamiltonian, but not satisfy either of these conditions. And I invite you to find such a graph. It's a very simple graph. So examples, here's a graph. It does satisfy the conditions of this theorem, Euler's theorem. I won't go through the details, it's just arithmetic. You add up the degrees of every pair of vertices. And so it is Hamiltonian. And here is a graph that satisfies the conditions in the corollary. These are just, they're not as strong. There are graphs that satisfy these conditions, but not this. But this is easier to determine. So it might be practical to try this condition first. If it fails, you'd still want to try this one. So that concludes our discussion of Eulerian graphs and Hamiltonian graphs. What's next is graph isomorphisms and planar graphs. So thank you for watching, and I hope to see you in the next video.